Curve. Okay. Gotcha. So here we go. We have talked about some very basic antiderivative rules, but here's the problem. Not everything is basic, is it? Sometimes we have some complicated functions. And in our derivatives unit, we had a lot of strategies to help us. We had the product rule, we had the quotient rule, we had the chain rule, okay? We really don't have that in antiderivatives. We just have our basic rules, okay? Now let's think back to our derivatives unit. We know that if we take the derivative of a composition, then we would get f prime of g of x times g prime of x. So if we think about what we were doing last week, if this derivative is this, then if we go backwards, the antiderivative of this would have to be the composition, right? Seems simple, but there's a lot of pieces we have to put together to figure out what our composition is. But essentially, the process of doing Usubstitution is trying to do the chain rule backwards. But we have to figure out what our composition is, what is f prime and g prime. Luckily, we don't actually have to identify those. We just need to understand how derivatives and antiderivatives function. Fun and stuff. Basically, what's going to happen is we're going to keep our eyes out for some sort of composition, okay? And what's really nice is if we have the inside of a composition and on the outside of the composition, we can find its derivative, then we can make a substitution to where instead of like multiple functions, we can just have one, okay? So what we're gonna do is we are going to look for a composition, and we call this Usubstitution. So if we have a composition, we are going to try to let u equal the inner function and see if its derivative lives on the outside somewhere, okay? If we let u equal g of x, does g prime of x live somewhere inside of our integrand? Can we make this all fit together? Okay. Right now I'm talking what seems to be gibberish, right? Yeah. Here in about 5 minutes, you'll be able to look at this and make sense of what I'm saying, okay? Would you like to share your smart aleck comment with the whole class? Okay. So I'm going to give you some instructions, like a step-by-step list, okay? This is something that you might need today, but you might not need like on Thursday. You're just gonna like have it figured out, okay? So this is what's going to happen. We are going to keep our eyes out for the inner function, okay? And we're gonna actually write u equals something. we're gonna look for our inner function, and u is gonna equal, like maybe u equals x squared, or u equals 15x minus 3. I don't know. It's gonna equal something, okay? Then what you're going to do is you're going to differentiate u so that you can substitute anything that's an x becomes a u. So we're gonna go from an integral with dx to an integral with du. Teachers in the hallway this morning. Well, Plunksy, but there's a theme. I can't tell if it's Ullery or Han down there. Okay. Now, once we have rewritten our integral, we actually got to go through the antiderivative process, but everything is u's. We didn't start out with u's, so we need to go back to our x's. So we know that u equals g of x. So we have to replace u with whatever we said it equaled in the first place. Okay. Guys, it's going to be 50 degrees tomorrow. I don't think it's, well, right. I will not make fun of you for wearing shorts tomorrow. I had a lot of guys wearing shorts last week, and I thought it was ridiculous. For me, is a lot different than
for guys, because you're like 30s or whatever, or like whatever it was last week. I mean, like in the 40s,
50s. 50s, I'll let my boys wear shorts probably. Yeah.
There's something about guys that are just like inevitable. They can wear shorts all the time.
Yeah.
Not.
All right, so here we go. This is our first example. Okay. X squared plus 1, the quantity to the 50th power times 2x dx. Now, before today, your only option would have been to expand x squared plus 1 to the 50th power and then multiply that expansion by 2x. Would you like to do that?
Yeah.
No. Okay. But what I see is that this is a composition. Do we have a function inside of a function?
Yeah.
Yes. And bonus, it's multiplied by another function. I'm saying a lot of weird things here. So like, this is what we're hoping for. Some sort of function inside of a function. And hopefully we're multiplying by something a little simple. Okay. So we actually have that, where our inside function for this composition is x squared plus 1. So what we're going to do is we're going to let u equal x squared plus 1. Okay. Now, what would the derivative with respect to x of u equal? Derivative is just 2x. Okay, and now here's what we have to be careful with. We are doing a derivative inside of an antiderivative. Okay, so we got to keep the process straight. Okay, now I am going to rewrite this as du equals 2x dx. Oh my goodness, this is so great. 2x dx. Do you see that? Right here. This is pretty fantastic. What we can do is we can take this right here and rewrite it as x squared plus 1 is u. So we have u to the 50th power. And 2x dx is the same thing as du. We have the integral of u to the 50th du. Now it's super simple. So u to the 51st times 1 over 51 plus c. Can you see that blue okay? It's what? Oh, okay, something new. I'm using like a different palette of colors today. Okay. It's calming, okay? It's a good Monday blue. What? Okay. Do you understand this? That's a no. Okay. So x squared plus 1, we said was u. So I replaced it with u. So we have u to the 50th power. Now, when I took the derivative of u, we rewrote du equals 2x dx from our derivative. Well, 2x dx is right here. 2x dx equals du. So I replaced 2x dx with du. So I have the integral of u to the 50th du. So take the antiderivative of u to the 50th with respect to u.
Oh, okay.
So we did that. Now, our original problem has x's. So we better rewrite our answer. We know that u is x squared plus 1. So our final answer would need to be 1 over 51 x squared plus 1 to the 51st plus c.
That's where I was lost.
Why do we still have u's? Okay, yeah, I don't want your answer to be u's. I want them to be x's. Isn't that nice how all those pieces fit together? Should we try another one? The answer is always yes. Here's our next example. Okay, remember we don't have a product rule for antiderivatives. So just having a product in general is problematic, okay? Now, like in our warm-up, we could distribute the two and be fine. Here, there's no distributing. I have 3x squared times cosine of something. Like there's no rewriting that. But since we have a product and part of our product is a composition, that's good. Okay, so if we have an antiderivative that does not follow a basic rule, and in there we see a composition, that's a good start. So since our composition is cosine of x cubed, then it's inside x cubed is what we're going to try to let u equal. Okay, now we know the derivative of x cubed is 3x squared. So I'm going to go just straight to writing this. Du equals 3x squared dx. We know we need that dx with the x's. So in the last example, I wrote du dx equaled whatever, and then multiplied the dx over. We're always going to need that dx with the x. So we're going to use our differential notation from way back in unit 3. Okay. All right. So if I take this integral, we can rewrite, well, the cosine of x cubed can be rewritten as the cosine of u. I have 3x squared dx left over in my integral. There's 3x squared dx right here. It gets replaced with Sudo. Sounds like a Star Wars names, right? Okay. All right, so the antiderivative of cosine. Positive, negative? Positive. So we have the sine of u plus c, but you're not going to leave it like that. You must change u back to in terms of x. So we have the sine of x cubed plus c. Like you can think about that in your head. Okay. This is why it works the way that it does. Okay. Now, we have had some pretty nice examples, right? Where exactly what we needed has been in there. Let me let you do one. It'll stay like that forever. Yes, that's what I was going to say. All right, you do this one for me. You don't know your basic trig antiderivatives. This one's gonna stink. Matt, you no longer have any sort of form in your hand. Yeah. Or like,
So you was like 2 minutes to 4, right? Oh, that's not right. It was like 2 minutes to 4, right? It's a great video. Is it like a
Yeah.
What? What?
integral, do you see it?
What?
8x cubed dx.
Oh.
So yeah, you just did it.
Oh.
So like when the du is just saying with respect to u. Like this dx right here, the antiderivative of sine of x with respect to x is negative cosine of x plus c. Like we never keep the dx. That's just saying, hey, this is a variable you're doing it with respect to. Okay. All right. Matt, did you use Usubstitution? Okay, what did you let u equal? Okay. So if u is 2x to the 4th, tune in what is du? Which conveniently I see right here. So we can rewrite our integral as secant squared u du. What is the it's like what? Is Easter? It's, you know, the middle of January. We're like, we need some color in our life, right? Okay, antiderivative for secant squared. So we have the tangent of a 2x to the fourth plus c. Did you get there? Okay. Turn to your neighbor, give them a high five. Everyone gets a high five. All right, so now, Dylan, what happens? No, I
We could just do like what we did for like for number. No, fine, I think we can do that.
we can't. We cannot distribute that x squared into the radical. Just write it down, write it down. So Aaron is really wanting to rewrite this like we did last week, but it's not going to be possible because we have addition or subtraction underneath of our radical. Okay, since that exists, we can't get those distributed through. What I do see, however, is that we have a composition and we have a composition multiplied to another function. So that's good because that could be a candidate for Usubstitution. So let's just say we wanted to try Usubstitution. What would we let U equal? And du would equal 15x squared dx. Okay, so here's the problem. I see x squared dx. I don't see 15x squared dx. Okay, so we can take this 15 and we can move it over to the du. 1/15 du equals x squared dx. And now we have a substitution that we can make. So the integral of u to the 1/2 x squared dx gets replaced with 1/15 du. And I just really like to put those coefficients outside my integral because but you can put it on the inside. I just put it on the outside. Sometimes it's easier to work with that way. Are we okay with what I just did?
I think after seeing
So our antiderivative u to the 3/2 times 2/3 plus c would end up as 2/45 5x cubed plus 4 to the 3/2 plus c. And if you're really unsure if that was the correct method, we could take the derivative of what I have here in gray and see if we get back to our original function. Okay. You don't love it?
I understand. I just don't.
Okay, so here's what I noticed, and I think this is something that's going to be helpful for you to notice. I noticed that I have a composition where inside I have a cubic function, and outside I have x squared, which is when we take the derivative, right? We want one less power, okay? That's kind of something to keep our eyes out for. Okay. Nathan, are you good with what we did here?
Yes.
Okay. Okay. Kylie, are you okay with what we did right here?
I just have a question about the 2.4.
Okay, so we have 1/15 multiplied to 2/3. Yeah. Okay, so I want you to look at these two right here. We can just put our pencils down for a moment. Okay, I want to look at, would these work for U substitution? Why or why not? So let's start with this guy right here. Okay, Isaac, I heard your no really loud. Why not? So if U equals 2x squared plus 3, we don't have this piece of any sort of x on the outside to replace with our dx. Okay, so in this problem, you would have to actually perform the square to the binomial and then have 3 separate terms for our antiderivative. It would not be too difficult.
Why couldn't you put it on the outside? Like 1 over 4x on the outside.
Because we're changing everything to u's. We don't want an x in there. Can we use U substitution here? Dylan, I heard you say no. So if my inside function is x cubed plus 2, then du would be 3x squared dx. And this is x to the first. We need an x squared. So U substitution is not going to work here. And we would have to actually multiply all of that out.
Would you like to divide over the 3 and like square root it? Or is that just like too complicated?
Yeah, that's not going to work because we'd still have that x. Yeah. I know, but you don't have the square root of du, and I need du, or yeah, and we need du. We don't want the square root of du. Yeah. All right. Last example, and we'll call it a day. We can do it with this one. Is this my last example? No, turns out it is. Okay. Is this a composition? Okay, that's good. Inside the composition is the function x to the 6th. So we're going to let u equal x to the 6th. Which means du is 6x to the 5th dx. What I notice, however, is that I have x to the 5th dx. So in order to replace x to the 5th dx, we will need to divide that 6 over to be with our du. So we have 1/6 integral sine of u du. Wyatt, important question for you. The antiderivative of sine, what is it? So this antiderivative is -1/6 cosine of x to the 6th plus c. Ooh. Now, we have dipped our toe in the water of U substitution. Tomorrow, we're going to look at problems that involve the natural log of x, e to the x. Then we're going to look at some like pretty heavy U substitution problems on Wednesday when it gets a little bit more complicated. Okay. We are working towards a quiz on Friday. Remember, at any time I could give you a rule quiz with our antiderivatives as well as a homework quiz.